सो नमस्कार जय जगन्नाथ मु सत्यजित मो विषय कहवाक गले मु हूँ जड़े एरोस्पेस इंजीनियर कहगले वैमानिक जंत्री तो एबे मु मोर मास्टर्स मास्टर्स करछि डिफेंस टेक्नोलॉजी कोलकाता यूनिवर्सिटी. So I joined through GATE and I'm currently working as a project associate with GATE.net for National Aerospace Laboratory CSI in Bangalore. So better जदि आपण ओडिया और या आप हिंदी मीडियम से हो या फिर आप CFD के बारे में ज़्यादा जानना चाहते हो or if you want to know anything regarding CFD from basics आपण मते मैसेज करि परिबे. You can approach me for any doubt. आप मुझे अप्रोच कर सकते हो. तो मैं ज़्यादातर हिंदी में बात करूँगा. That doesn't mean that I don't know English. I am fluent in English. I think it will reach to all of the people of the nation. So I'll start with both Hindi and English. Let's begin. So this is the first lecture on CFD. So start from basics. This is a lecture which is going to be introduction to computational fluid dynamics, or which will generalize call it as CFD. So basically CFD means computational fluid dynamics. So we'll learn about what is CFD, what is the uses and other basic things. So it is an introduction lecture, and it is going to be the lecture number 1. So what is CFD? CFD is used to compute to solve a wide range of problems in fluid flow and heat transfer. So computational fluid dynamics doesn't mean it's only limited to the fluid or air. We can also do the heat transfer for formulation and modeling. We can also do the projects, or we call it problem solving for heat transfer. CFD ये है. CFD को हम कंप्यूटेशनल फ्लूइड डायनामिक बोलते हैं, जिसका यूज करके हम फ्लूइड का जो तरल पदार्थ है, जैसे वायु हो गया या जल हो गया या पानी हो गया या आपका फ्यूल हो गए, मतलब जैसे केरोसिन या जो आपका पेट्रोलियम कैसे फ्लो कर रहा है या कार्बोरेटर का अंदर कैसे जा रहा है, ये सब नॉट जस्ट फ्लूइड. आप इसके साथ साथ हीट के ट्रांसफर भी आप वैल्यूएशन मतलब कैलकुलेशन वगैरह कर सकते हैं. So where we can use CFD? So we can use CFD in a large domains, like large range of domains. So हम CFD को बहुत मतलब जैसे एरोस्पेस हो गए, नेवल, फिर आपका पाइप में फ्लो, ब्लड, ऑर्गेनिक चीज़ों के अंदर सबके ऊपर. So we'll go by one level. So first is application in aerospace. So mostly I am from aerospace background, so the lift, drag and the shock waves, flutter and other things, like so many things you can find the variation of lift, and you can find wave drags and how the flow is going over the surface of a high speed missile or a high speed space vehicle or a aircraft. So next is CFD can also use in applicants like the cold storage devices like freeze, refrigeration, for preserve, like for seed preserve things. So I've taken the example of the refrigerator. Also in the like cold storage of our earth, like we have a cold storage in North Atlantic and South also. So there we are preserving the seed for some time. Like if there is a disaster, like large natural disaster, and you will end up with a we call it millets. So we have the storage where we have already kept our millets for further like research and development. So next thing is automobiles. So as you know, automobiles is a large variation is going. So earlier it was a blunt body like rectangular shape. Now it's getting aerodynamic shape to reduce the fuel consumption. Also, it can improvise your mileage. Also, the same time the speed cars we can use that. So here the engine engine heat out is transferring undercarriage of the vehicle. Also the airflow over the vehicle, the aerodynamic of the vehicle, and the engine heat transfer, the AC, the ventilation things inside the uh, cabin. So like the biomedical things. So in biomedical things, the eye, how the temperature is variation is happening over the eye, also like medical blood pumps. So so many bio, like not just medical, like artificial hearts and other things we can do the simulations. Also for lungs and the nasal cavities, I will come back to that later. So for chemicals, how the mixtures are happening, like the steering and other things are doing, like evolving in the chemical process, how the chemical is getting mixed up, or how the fluid is getting mixed up. So that we can visualize by the help of chemistry, like a chemical, for chemical CFD for chemical processing. So heat treatment and other thing also you can do. Next thing is the ventilation and aeration. So in ventilation you can model the large office for the ventilation, and also for the vent, which is also a good thing for the equatorial region. Most of the Arabian nations and the like, toward the equator the temperature is large. So to work in a effective domain, the temperature should be controlled over the office room. So further the ventilation and other things we can model it by using CFD. So hydraulic, not just dam, like so many like large storage dams and reservoirs like that are we'll come to the like energy harvesting later. So in hydraulic we can also go for that, and fluid flow through a pipe, other things we can do. The marine things like mostly the submarines or the frigates, how the um, fluid is flowing over the hull. Another thing we can analyze by using the CFD. So oil and gas inside the tanker or the oil field, like offshore oil rigs which are present in the oceans or near to the shores. So how the waves of the sea is affecting their pillars, and also during the drill bit we are using the flow and oil for cooling the drill. So those things also you can simulate. This is a water tank where the fluid how it is like fluctuating, like the level is fluctuating while it is moving. That also you can analyze that. So also not just small, for the thermal power plants, also the flow blower, the same time for the what, for hydraulic, for energy generation, also for the propeller of the submarines. So many like power generations. So there we can also see the fluid flow, and whether it is creating the turbulence which will reduce the either one energy, it will cause a reduction in energy harvesting, also to the output when if this is not streamlined for a propeller of a submarine, so it will be a drawback. So you can change the design. Next thing in the sports, not just swimming. Also in crickets, the cricket ball, the spin of the ball, the swim of the ball, also the swimmer, the hand position, and for a cyclist, the speed. All are the domain where you can use CFD. So from this, we can got a large domain where you can use CFD. Also, so many are left out. So next, the important factor which is influencing the CFD is like the rapid growth of computing power. So first of all, without making a prototype or the real physical model, you can do the simulation of any uh, design like a 3D model stuff using CFD, and you can find the fluid flow over it without going for the physical modeling. So it's saving a lot of time, and also the computing power is very high. It depends on your processor. If you have a if you are in a lab, there will be a central like a high precision computing things. So there you can do large computing power. You can go for in a very like micron level grid size per mesh. So also the numerical methods are improved. So you can get the precise results. Uh, More efficient is the numerical techniques. So advanced visualization tools, you can visualize not just the streamlines, you can also visualize the vertices, vectors, then contour. So many things you can achieve by using one error. So increase in computational power, as you know, like the computational, like the world is going to a new era of computation. There are supercomputers, supercomputers, quantum computers. So you can compute in very short time with high precision things. So need of high performing computers. So first of all, we'll go through a car. So the vehicle to design that we are spending a lot of time, and you know like the manufacturing assembly and material selection, so many stuffs are there which will make the vehicle heavy, and to move the heavy vehicle we need a powerful engine. So for engine we need fuel, and all the fuel stuff is all depend upon the draft causing by the vehicle. It will, if the vehicle is blunt, it will consume more fuel. At the same time the customer have to pay more, and he will find some difficulties, or he will put his he will not will be not interested to buy your stuff if it is consuming more fuel and it's not pocket friendly. To solve everything, we can design a better object which will be pocket friendly and consuming less fuel. Indirectly, it should be efficient. For that efficiency, we have to improvise the streamline over the car, but which will automatically reduce the drag. So the next thing is it will generate a highly reliable models. So you can go for optimization also, which is for the vehicle dynamics and the thermoaerodynamics. So for vehicle dynamics, you need the output of the CFD, and for thermoaerodynamics also, thermoaerodynamics directly related to the CFD. For vehicular dynamics, like flutter, vibrations, and aeroelasticity, that like structural elasticity, you need the CFD data. So the best thing is CFD is low cost, and you can easily do the analysis in short time without going for the model. Also, it have the ability to simulate the real time conditions, like minor error will be there. So first thing, cost, low cost. So using physical experiments and tests to get essential engineering data for the design can be expensive, which can be minimized by using CFD. So computational simulations are relatively expensive, and costs are likely to be decreased as computer become more powerful. So if your computer is more powerful, no need to go for number of runs. In one run, you can get your precise data. So it will consume your computer cost to be more, but for a long time it will be a solution. So speed computer like computational time is dependent on core of processor. So CFD simulation can be executed in short period of time, like 5 minutes for, it depends upon the grid size and number of iterations you are given. So quick uh, turn, uh, turnaround means engineering data can be introduced earlier in the design processing. So no need to recreate the design or modify to the physical model, which will cost you more. The mold, it will cost more if you are changing the mold each time. So better before in the pre-design stage. So but that time only we have to change. So mainly flow and heat transfer cannot be tested. So we can do that in CFD, which also you will get a better visual. So like the same one example, if there is a missile, if we are going to Mark 20, it's not physically possible till now to run a missile at 20 Mark, but you can do the analysis by using CFD. You can give 200 Mark also if physically there is no significant, but you can go for any run. Same time, no need to do a nuclear disaster. But you can see if there is a nuclear disaster happening to a site where the pre-existing structure is there and how it is affecting to the surrounding. By taking the data, you can change the location of, like you can predict the location where you have to establish the nuclear power facilities, so to prevent the disasters. Even there is a disaster, it will cause the loss. The CFD provide the ability theoretical simulation for any physical conditions. That you can model anything, just all you need to set a proper boundary condition. The advantage of CFD, the ability to simulate ideal conditions. So all things, it depends upon your boundary conditions. The physical process provides ability to isolate specific phenomena for studies. So whichever the domain you want to study, you can do the physical modeling, you will get the results. For example, a heat transfer process can idealize with adiabatic, constant heat flux, or constant temperature boundaries. That I told, like any boundary condition you can assign and you can do the analysis, which might not be possible in physical, physical process. So compressive informations. So for experiments, only permit the data to be extracted at limited numbers for locations in the system. So like if there is a small part inside the gas turbine engine at the tip of the blade, if you want to test the temperature, it's not possible physically to go and there and test. But while doing a CFD analysis, you can do that. So CFD allow to analyze, like you can get the data from any position of your model. CFD allow the analysis to be extreme a large number of locations or regions of interest. Wherever you interest, you can take the data. You can vary or simulate. So limitations of CFD. So each have benefits and demerits. So physical models, CFD solutions rarely opens the physical models of real-time world process. So definitely the real-time process will be numericals, method and other things. You will get different solution compared to a physical like CFD model, because we may not model the turbulence, compressibility effects, chemical chemistry of the compositions, those things, and multi-phase flows, like for a flow like the flow at the combustion chamber, like the air and fluid both combustion, those things will be difficulties, but nowadays it is getting improvised and we are able now, mostly we are able to solve those things. But definitely we can't model the physically happening things into a model to the accurate point. We can get a result up to 95 to 98%, but we will not get the accurate result to 100%. There will be some error losses, those we might not file in our boundary conditions. The solutions that are obtained through the CFD can only be accurate as physical model on which they are based. Like that I told, if you are exactly given the boundary conditions and the process that is happening physically to the model, you will get the most accurate data to the end. But it might not be exact. There will be exact and accurate. So numerical errors. During solving, we are mostly dealing with two errors, which is round off and truncation. Round off is basically we are neglecting the decimal places after like 5, 6, or if this is a 26, 64 bit. After that, after the 16th position, 10 to the power minus 16th, we are neglecting the like we are neglecting the decimal numbers. So that is correct, causing a round off error. So similarly, the truncation error is due to the approximation in the numerical methods. So we are giving some parameter to be um, approximated to something. So that is causing a truncation error. So round off errors will always exist as the we can use a 32 bit or 64 bit. For 32 bit is 8 digit. After the decimal 8 digit, it is might be neglected. Depends upon your like, accuracy you want. That is very less. So truncation error will be go to the zero as the grid refines. So the turbulence flow k epsilon k omega is all depends on the grid, like the mesh quality and other things. So the mesh, if it is highly dense, the truncation error will be negligible. Same time, if you are going for a large mesh, the truncation error will be more. The approximation is in that order. So the limitations of CFD, like this is the second limit, like the boundary condition you have to set it properly. The computer research, like the speed, like even with a the new computers, though the computer is very fast and large storage media, the simulation of complex engineering system could still require more computational resources. Like the processors we are using, it's having just 8 to 10 core processors or like 16. For the industries, it needs some more like large computational power. So there are some 50 plus cores are available. Similarly, the boundary is the physical model. The accuracy of the CFD solution is only good as the initial or the boundary conditions. I have forgotten the initial. Both initial and boundary condition, also the process steps must be modeled properly. Then only you will get the accurate data. So as I have given the like examples. So for a boundary condition, if you have set if you have set the inlet, if there is no wall you have given, the flow will move simply. But with wall there will be viscous effect, and it will cause a boundary layer things. So as you told, if the flow is supplied to the domain of by a pipe, you use a fully developed profile for the velocity rather than assume uniform conditions. So this is a geometrical model of a aircraft nose without the what do you call it? Without the glass, like without the cover. So you can simulate it and after messing. So physics. The CFD code typically designed for resolution of certain flow phenomena like viscous or inviscid, like the basically the CFD we are studying, like fluid dynamics we are studying, which is it depends upon the Reynolds number. Turbulent or laminar, that is also depends on the Reynolds number. The Mach number is also come into picture when it is incompressible or compressible, because under 0.33 Mach it's incompressible, the flow we are considering, and after 0.33 it will be compressible. Like that we will go for multi-phase. So basically the Strauss number and Nusselt's number, Prandtl's number, then Froude's number, those like chemical reactions, free surface flow, thermal density, other things are coming into picture. So model requirements depends upon which physical phenomena is important. So if you are going for draft, there will be heat transfer also. There will be Nusselt's number coming to picture. You can turn on your energy equation and you can get temperature. Also, You can neglect them and you can go for the turbulence and laminar model, where you are more focusing over the velocity, like the flow profile, like the bounded things, or the uh, Mach and Reynolds numbers. So the basics will start from the next lectures, which is nothing but the Reynolds transportation theorems, the transportation equations, and the interactions. So also I told we can use it for biomedical facilities like the nasal drops or the asthma, like the drugs delivery devices also can be modeled by using the human path, like the internal part of the body through which it is flow. The gas particle flow in the boiler also can be modeled. So this is a like fly ash velocity and the concentration distribution. So like after boiler, the fly ash can be accumulated to reduce the environment pollutions. So numerical issues. The computational solutions of the governing equations are restricted. Method depends upon the model of equation and physics. So several components of formulations will see the discretization and linearization. Then it's come to the assembly of the system of algebraic equations, solution of the equations. So basically, unsteady 3D runs equations have many issues because the errors, the truncations, and round of errors are like we are considering most. The first numerical techniques, like basically the background solving the matrix. Build metric equation may take point across boundaries, like boundary layers, including the boundary conditions. So mostly the first matrix is on the boundary conditions, and these are the physical parameters, and this is the output. So in no slip zone we are getting, and its edge velocity we are getting, which is maximum and minimum respectively. So these specially types of matrix equations known as triangular uh, tri-diagonal systems. Sorry, tri-diagonal systems. So which can be solved directly. It means like you can also do the simulation without opening CFD, and you can check the boundary conditions by solving the matrix. And this is the background of the CFD, what is going on. So whenever you give the boundary conditions, it will generate a matrix and it will go for solving to a solver. And solver will mostly deal with the matrix solutions. So before that, the eigenvalue and eigenvalue and eigenvectors, if you know how to solve them, it will be a plus point in your solving. Softwares. So we have so many softwares like for ANSYS we have CFD software like Fluid Flow Fluent, iSpeak, CFX. So like that we have Star CCM. Building upon physics, modeling, and numerics, there are different softwares. So two types of available softwares are commercial and research for commercial Fluent, CFX, and Star CCM we are using. For research, we are using CFD cores in university institutes. There are so many different cores which are developed by various of institutions. You can use them. Like you can also go for OpenBSD for a small type of CFD analysis. So it's basically they are solving the matrices, especially coding for parallel computing. So I told the matrix is very large. You can also go for the parallel computation to reduce your sample time. The next thing is after the modeling and solution, the next step comes into picture is the post processing. So in post processing, generally we are visualizing the data and the data reduction, also the analysis we are doing there. So calculation for derivatives or variables, the visualization of 2D XY plot, or also you can go for 3D plots. Simple 2D contours, streamlines, 3D contours, the vector plots they told. So so many things you can do. So research and developments. So first of all, we'll go for mathematics, which is the physically modeling we are doing. The computational fluid dynamics, which is the engineering stuff, and the computer science. So the three things are basically the linkage between the computational fluid dynamics, experimental fluid dynamics, and model development validation. So the computational computer science is a link between these two. So I'll go for the end. So the computer science, this is a between these two. So engineering is linking between the experimental and computational fluid dynamics. Mathematics is creating the model and it's the it's the intermediate between these two. This is the flow how we are doing the argument. So first, if there is a problem, it can be modeled mathematically, and also the engineering approach to do experimentally and collect the data. The computer science will link the experimental and how valid, and it will help to validate. The next thing is research on engine flow. So you can check the physical processes, exiting models the frame, spray break flow, droplet drag, wall impigmentation, turbulence, uh, then the conversions, stow, canoics. So many models are exiting. So you can use the K epsilon models, then K omega, slide model, droplet distribution models, splat algorithm models, methods. So many are there. We can apply to the design things. So fluid structural interaction. If you are talking about the aeroelasticity, basically. So first we will do the CFD modeling. Then we will also do the finite element analysis. So the data from the output of the CFD modeling, that is basically the turbulence, pressure waves, the force distributions, temperature, the flux, the fluctuations where it is taking place. So those things can be given to the FEA model as an input for the vibrations, acoustic, noise, vibration, acoustic or noise, deformation, and stress calculations. At the same time, if there is a FEM model, you can give the data for the self weight and gravity, those things you can give in fluid mechanics, fluid analysis to get a better accurate results. So innovative CFD and CAD optimizations. So in the end, we are coming to conclusion that to reduce the money and the efforts to go for several iterations for concluding that this is the best way to design a product. So before that you need both finite element analysis, CFD, and before that you have to do the CAD modeling, 3D modeling. So it depends upon your designers and your outcome results from the CFD. You can go for the modification of the 3D model, which will reduce your design cost and other things. And also it will save your times. So basically computational fluid dynamics, you can see the flow distribution, the efficiency, performance, and thermal analysis you can do in CFD. The same type of computer aided design, you can change the thickness, like the fineness ratio, the geometrical shape, which is the geometrical shape, the materials, and for the CFD, like the thermal conductivity and the porosity, the surface finishings, the manufacturing technique which you have to use for that to get that much fine surface finishing, like whether you have to go for CNC or you have to go for lathing, those things you will conclude from the CFD CAD optimize. So the next is the end of the lecture. So see you in the second lecture. Till that, Jai Hind. Thank you. If you have any doubt, you can message below. Thank you for watching. Jai Hind.